Hello everyone, let's analyze. So today we're going to talk about Taylor's theorem and local extrema. You might remember Taylor's theorem as a way of approximating, in a certain sense, functions by polynomials if the function was sufficiently differentiable. And we're also going to talk about local extrema, local minimum and maximum of real valued functions. So just as a bit of a review of where we've been, let F map a subset of Rn to R. Then the first derivative, assuming the first derivative exists, at some point x and u is a linear map from Rn to R. Now, a linear map from Rn to R, that's equivalent to a Rn by 1 matrix. Or a matrix in Rn by 1. So we might write the derivative as a n by 1 matrix, and for a function that is real valued, this is equal to the gradient transpose, which is the horizontal array of all of the partial derivative in every canonical direction. So when I say the derivative of f of x, right, operating on some vector u, that's the same thing as saying the gradient of f at x transpose times u, right? It's the same thing. Now the second derivative at x and u, again, assuming such a thing exists, that is a linear map from Rn to, right, because I'm taking the derivative of df. And of course, df for each x is a Rn by 1 matrix. And of course, we could say that this is equivalent to a Rn by 1 matrix. Of course, n by 1 just means a n by n matrix. Of course, another way of viewing a linear map from Rn to Rn by 1, this Rn by 1 implies that this is representing a map from vectors of n dimension to vectors of 1 dimension, or to scalars. Right? Because it is, because the first derivative is a linear map from Rn to R. Another way to think of it is it's a bilinear map from Rn by Rn to R, because it maps linearly a vector in Rn to something that's Rn by 1, which itself represents a linear map from Rn to R. So I have two linear maps being performed. That's what's represented by this Rn by Rn. I can input two different vectors and map them linearly to a number. And the second derivative therefore can be applied to let's make them different. Let's call this v, in fact, so we don't confuse it with this x here. It's the same thing as v transpose times the matrix representation of the second derivative, which we call a Hessian, evaluated at x times y. Of course, it's the Hessian with respect to f. So this is the Hessian. It is the matrix representation of the second derivative, right, which we discussed in the last lecture. So if the first derivative is a linear map, the second derivative can be thought of as a bilinear map. Well, then the third derivative is a trilinear map. So the third derivative at some x in u is a linear map from Rn to Rn by n by 1, which of course is the same as just saying Rn by n, but I'm leaving that by 1 just to imply that it maps a n-dimensional vector and another n-dimensional vector to a real number. Right, that's the destination of this map. Again, we could think of this as a trilinear map from Rn by Rn by Rn to R so the third derivative would map u, v, and w, each vectors in Rn, and the outcome of that would be a real number. Similarly, the jth derivative, assuming such a derivative exists, at x and u is a J-linear map, right? Just as the third derivative is a trilinear, the second derivative is bilinear, and the first derivative is linear. The jth derivative is a J-linear map from Rn by Rn by Rn. There are, you guessed it, J of them. Right, so this is the set of all J tuples, right, where each entry in this J tuple is a vector in Rn. And of course it's real valued because the original function we're dealing with is a map to R, or a real valued function. Now, a bit of notation. I'm going to let H parentheses J represent the J tuple of all H's. H is in Rn. So this is a J tuple. So this would be a bit of shorthand. When I say h to the parentheses j, what I mean is a j tuple. So for example, the second derivative of f at x applied to the 2 tuple is, well, according to my derivative of how I apply the second derivative to 2 vectors, it's equal to the first argument transpose times the Hessian matrix times the second argument. So this equals H transpose times the Hessian at x times H. So a few definitions so that we're all talking the same language. We say that a function is called class CR if the first R derivatives exist and are continuous. By way of notation, we'll use v to the parentheses j to refer to the j tuple of the same vector v. Okay. So Taylor's theorem, right? Which again, I would imagine you've probably seen in some form before for real valued functions of real numbers. This is a generalization of functions that map Rn to R. Suppose f is class CR, and let the interval x0 to x, remember that's the line segment connecting x0 and x, be contained in U. Then there exists a C in the interior of that line segment such that f of x is equal to f of x0 plus the scaled sum of the first r minus 1 derivatives of f at x0 times the j tuple x minus x0 from j equals 1 to r minus 1 plus my remainder term. And my remainder term is scaled by 1 over r factorial, which is a small number if r is big enough, times the rth derivative of f at some point c. So this last term is my remainder. I would like for it to be small, and in fact Taylor's theorem guarantees me that it's small in the form of this limit. The limit of my remainder when divided by x minus x0 to the r minus 1 power is 0. So by the way, this term in red is what's referred to as the r minus 1 order Taylor polynomial. Right? In fact, it looks like, and then you can think of it as a polynomial, right, on x minus x0. So let's prove the statement. Okay, so let's prove Taylor's theorem, and we'll do it by induction. K is equal to 1, right? So in Taylor's theorem, we have a statement for the r minus 1 Taylor polynomial and the r minus 1 remainder, which involves the derivative or the rth derivative. So we're going to work our way to r. We're going to start with k equals to 1. So then by the mean value theorem, I know that f of x minus f of x0 is equal to the derivative of f at some c times x minus x0, right? For some vector c in the interval x0 to x. Remember, this interval is the set of all convex combinations of x0 and x, but not equal to x0 and x. Now the limit, right, I need to show a limit statement to show that Taylor is true. Well, 0 is less than or equal to the absolute value d of f of c times x minus x naught divided by the norm of x minus x naught raised to the power of 1 minus 1. Now, I need to show that the limit of this is equal to 0 as x approaches x naught. Well, of course, this raised to the 1 minus 1 power is just 1. And I get the derivative of f at c is just the gradient transpose times x minus x naught. And now this is an inner product. I'm taking each entry in the gradient and multiplying by each entry in this difference. Right? That's an inner product, so by using the Schwartz, the Cauchy-Schwartz in fact, it's less than or equal to the norm of the gradient times the norm of x minus x naught. And of course, this is constant because, well, the derivative is well defined. At c, it's a continuous function because, again, we're assuming that our function is of class R. So this is bounded, and of course, this goes to 0 as x approaches x naught. So this goes to 0 as x approaches x naught. Okay? So we can say that we've proven the mean value theorem if R is 1. If R is 1, we've proven the mean value theorem. Okay. Now R is not 1, R is R, so let's work our way towards it. Let's look at for k equal to 2, just to get an idea of how this is going to work. And then after that, we'll use an induction step. Now, for the sake of simplicity, let's define h to be x minus x naught. Then f of x naught plus h minus f of x naught. Well, by the fundamental theorem of calculus, this is equal to the derivative with respect to t of f of x naught plus t h. Now, notice what I did here. I made this a function of t, and f is real valued. So if I think of this as a function of t, this is just a continuous mapping from t, from a real number to a real number, right, from t to f. I can take a derivative of it, I can take an integral of it. And the fundamental theorem of calculus tells me this is, right, when f of x naught plus 1 times h, which is f of x naught plus h, minus f of x naught plus 0, which is this term. Now, what is the derivative of this? Well, we know by the chain rule, this is equal to the integral from 0 to 1, the derivative of f at x naught plus th, plus the derivative of the argument. Of course, the derivative of the argument with respect to t is just h. And remember, this is still a real valued integrand because the derivative is going to be a map of from Rn, which h is, to r. So the derivative times h is real valued. In fact, it's equal to the gradient of f at x naught plus th transpose times h times, and here's where the main cleverness of this proof comes in, the derivative of t minus 1 dt. Now, hopefully you've noticed that the derivative of t minus 1 is 1. So all I did to this integrand is multiply by 1. But now I can compute this by using an integration by parts. We'll let this be u. We'll let this be dv. the derivative of u with respect to t is equal to, remember, the gradient of f transpose times h, right? That's the derivative of f. And now I have to take the derivative of that with respect to t. So I'll get the second derivative, evaluated here, times h. And then the chain rule says times the derivative of the argument with respect to t, which is h. Which, by the way, is just, right, this is a bilinear map of h and h. Right, this is just h transpose times the Hessian of f at x naught plus th times h. And remember, h is basically the vector giving me the difference between x and kind of my Taylor anchor, is the way I like to think of x naught. Of course, another way of thinking about taking the derivative of u, or another way of seeing that this result is true, is, well, u is equal to the sum from j equals 1 to n of all my partial derivatives of f evaluated at x naught plus th times the entries of h. Right, that's just from a linear algebra perspective, that's what that product looks like. And so if I take the derivative of it, I'm taking the derivative of this sum. And if I take the derivative of this sum, well, I'm treating each of these like a real valued function of a vector. Of course, I'm taking the derivative with respect to t, which requires the chain rule. I need to take the derivative of this with respect to the vector times the derivative of the argument with respect to t. So for each of these, I'll essentially get the gradient of these, but for each xj. So I get from k equals 1 through n, the sum from j equals 1 through n, right, the derivative of the derivative times x naught plus th times hj times hk. And, well, these are exactly the entries of my Hessian matrix. And to take this double sum of all the entries of my Hessian matrix times the entries of h, that's precisely what this bilinear map to a real number is. It's exactly the matrix times h and then times the transpose of h from the left. Of course, we see that we have du, and v is, of course, just t minus 1. So let's continue with computing this difference. By using integration by parts, I get u times v evaluated from 0 to 1 minus the integral from 0 to 1 v du. So v is t minus 1 and du is this term here, h transpose times the Hessian at x naught plus th times h dt. And that's equal to, well, at 1, this is equal to the gradient of f at x naught times 0 minus, right, at 0, the gradient of f at x naught plus 0 times negative 1. So the two minuses give me the gradient of f at x naught Oh, I'm missing an H, right? Transpose. And there's an H in there because that's part of the U. So I dropped an H. I need the H. Because remember that this is row valued. I can't get a vector here. It wouldn't make sense. Minus, I'm going to distribute this minus. So I get, just switch to here, 1 minus t, H transpose HF of x naught plus TH times H dt. Now we know from a result in real analysis 1, which can be thought of as a generalized mean value theorem for a continuous f and g on a beta r such that g is positive there exists a c in the interior such that the integral from a to b of f of t times g of t dt equals f of c times the integral from a to b of g of t dt. Okay, so you should remember this result from real analysis 1. We can think of it as a generalization because if g is equal to 1, then this is exactly just the mean value theorem. So let's apply this result to here. We can consider 1 minus t to play the role of g from our theorem because notice that it's positive or, well, non-negative on the interval from 0 to 1. So finally this gives us f of x naught plus h minus f of x naught equals the gradient of f of x naught transpose h plus h transpose times the Hessian of x naught plus some value theta times t times h times the integral from 0 to 1 of 1 minus t dt. Okay. Now we're going to call this parentheses needs to go here. We're going to call this vector c, right, where theta is in the interval 0 to 1. Right, we can see that c is between x naught and x naught plus h. And of course, x naught plus h is x, so c is between x naught and x. This integral, straightforward to compute. It's 1/2, right? It's just the area of a triangle of height 1 and base 1. So let's put this all together. F of x naught plus h equals f of x naught plus, now remember the gradient transpose, that's just the derivative evaluated x naught times h plus, and the h transpose times the Hessian times h, that's just the second derivative of f applied to the 2 tuple and this is evaluated at some c, where c is between x naught and x naught plus h. Okay, so this would be my first order Taylor polynomial or Taylor function. This is my remainder. Okay, now I still need to show that my remainder, oh, I'm missing times 1/2 because of this integral. Now I need to show that my remainder satisfies the limit condition. So I know that 0 is less than or equal to the absolute value of my second derivative at c applied to the 2 tuple of h divided by 2 times, right, x minus x naught, which I've called h, to the power of 2 minus 1. Now this equals h transpose times my Hessian at c times h divided by 2 times the norm of h, and this is less than or equal to the norm of h times the norm of the matrix at c, which we know to be bounded because it's continuous, times the norm of h again, divided by 2 times the norm of h. All right, so we have a norm of h squared in the numerator and a norm of h in the denominator. So this cancels. And we see that since this is some number, this goes to 0 as h goes to 0, which is to say as x approaches x naught. Right? So we've proven the limit condition of the Taylor statement. So now we've shown that if r is equal to 1, Taylor's theorem is true. We've even shown if r is equal to 2, Taylor's theorem is true. Now let's suppose it's true at k, and let's show that it's true at k plus 1. Right? It's true for r equals 1. It's true for r equals 2. If I can show this step works, that means since it's true at r equals to 2, it's true at r equals to 3. If it's true at r equals to 3, it's true at r equals to 4, and so on, forever until I run out of differentiability. So when I say Taylor is true at step k, what do I mean? Well, I mean that I can write f of x to be equal to f of x naught plus the sum from j equals 1 to k minus 1, because I'm at the kth step. K is some arbitrary number less than r. One divided by j factorial times the jth derivative of f evaluated at x naught times the x minus x naught j tuple plus 1 over k factorial times the kth derivative of f at some c times the x minus xj k tuple. Okay, so I've shown that this is true. Now I need to show that Taylor works if if I extend k to k plus 1. Well, that's equivalent to showing, right, I need to show that this is equal to one over k factorial times the kth derivative at f of x naught, right, not some arbitrary point c, but at x naught, times the k-tuple of x minus x naught plus my kth remainder term, right? This is the k minus 1 remainder term because it's what remains after my k minus 1 expansion. The k plus first derivative of f at some value c times x minus x naught k plus 1 tuple, right? If I can show that this remainder term is equal to this, then I've proven that Taylor is true at k plus 1, supposing that this equality is true. So let's see if I can do it. So again, let h be the difference x minus x naught, just for simplicity of notation. Then 1 over k factorial times the kth derivative at c times the k-tuple of h. Well, that equals dk of c times the k-tuple of h divided by k minus 1 factorial, of course, times 1 over k. Well, in fact, this is equal to 1 over k, which is why I get equality here. And then, of course, using the same generalization of the mean value theorem, I get this is equal to the integral from 0 to 1 minus t to the k minus 1 divided by k minus 1 factorial times this, but now evaluated at the integrand variable. Times the h k-tuple dt. Again, we're going to use integration by parts to get that this is equal to 1 over k factorial the kth derivative at x naught times the k-tuple of h plus the integral from 0 to 1 minus t to the k, that's going to be the v to this dv, divided by k factorial. This is u, so here's going to be my du, right? It's going to be a higher order. X naught plus th times another h. So h to the k plus 1 tuple dt. So again, I'm using the same integration by parts. We went over the details already. And again, using the same generalization of the mean value theorem. This equals 1 over k factorial times the kth derivative evaluated at x naught times the k tuple of h plus this evaluated at some point c, right? Or for some theta between 0 and 1, and I'm saying c is equal to that x naught plus theta h times my k plus 1 tuple times the integral of this, which is just 1 over k plus 1 factorial. Right, which is exactly what I needed to show my remainder to be equal to. Right? So, am I done? Almost. Right? Now I need to show the limit condition. Right? I need to show that the remainder goes to 0 as x goes to x naught. In other words, I want to show that my Taylor polynomial approximation is in fact a good approximation so long as x is sufficiently close to x naught. 0 is less than the absolute value. Right, this is a k plus 1. This is a k plus 1 linear operator, right? Like bilinear, trilinear, it's k plus 1 linear. Right, times the k plus 1 tuple. Divided by the norm of h to the k, right, or k plus 1 minus 1. And this is less than or equal to the norm of d to the k plus 1 of c times h to the k plus 1 divided by h to the k. Now, why can I say that this is true? Well, because this is a linear operator. So just like any linear operator, I can define a norm, right, by applying a maximum that it distorts the unit ball, right, in k plus 1 dimensional space. Right, just a matrix can be thought of as a linear operator, and that's the definition of the norm of a matrix. It's the maximum of a times x, where x is unit length. So if I take all of these to be unit length, I say what's the maximum this can make it, and that defines a norm. And since this is continuous, a linear norm, or a norm of a linear operator is bounded on a finite domain. So this is some bounded number. This cancels with this. And of course we see that this goes to 0 as h goes to 0. And now we have satisfied our proof. So let's work out an example. This will be part example and part exercise for you. Let f of x equal 3 times e to the x1 minus 2x2 times the cosine of 2x1 x2 minus x1 x2. So let's compute the second order Taylor polynomial, or Taylor function, expanding around x naught is equal to 0. Well, the derivative of f evaluated at 0 is equal to the matrix, the derivative of f evaluated with respect to x1 evaluated at 0. The second entry of my matrix is the derivative of f evaluated at x2, or the derivative with respect to x2 evaluated at 0. Okay, so I'll let you compute those derivatives and evaluate at 0. What you would get is 3, -6. Right? Once I evaluate the derivative at a point, right, I get a matrix, right, 1 by 2. Of course, I can also think of this as a mapping from vectors with 2 entries to numbers. The Hessian evaluated at 0, right, which represents my second derivative, is equal to the matrix of second derivatives evaluated at 0. Now, we also know that this function is sufficiently continuous that these two entries will be the same. So I'll let you go through and compute this derivative and this derivative and this derivative. You don't need to compute this one because you'll get the same thing as here, and then evaluate each of these at 0. You should get 3, -6, -6, 12. That means my second order Taylor function is equal to f of 0 plus df of 0 times x plus x transpose times my Hessian evaluated at 0 times x. And I also know that the limit as x goes to 0 of my remainder function divided by the norm of x to the 2 minus 1. Now, what is my remainder? Well, it's just f of x minus my Taylor polynomial right? Carry that limit over equals to 0. So this gives me an idea of how close this Taylor polynomial is to my function when x is sufficiently close to 0. I'm sorry, this should be 3 minus 1, which is of course 2, because my remainder term involves the third derivative. In other words, this is the Taylor expansion applied to r equals to 3. That gives me the second order Taylor polynomial. So let f map Rn to R. Well, then the local extrema is exactly what you think it is. A local maximum is when f of x naught is bigger than f of x for all x in some neighborhood or in some open ball of radius r. And similarly, f has a local minimum at x naught if there's some open ball, so that for every x in the open ball and in the domain, f of x naught is less than or equal to f of x. Now the set of local minima and maxima are called the relative extrema. Let's define what a critical point is. And of course we know that critical points are related to local maximum and minimums. So let f mapping a subset of Rn to R be differentiable on U. Then x naught in U is a critical point if the derivative of f at x naught is 0. Recall that the derivative for such functions is the gradient transpose. So oftentimes in other texts you may see that a critical point is defined when the gradient of f at that point is 0. But of course it's the same thing because one is just the transpose of the other. the first derivative test. Now, let f map an open set U in Rn to R be differentiable at x naught. If f has a local min or max at x naught, then x naught is a critical point. That is, the derivative is 0. Now, it's important that we understand the direction of implication. If I have a min or max, then the derivative is 0. Now, just because the derivative is 0 does not mean I have a minimum or a maximum. Of course, the first function that should pop into your head on the real line would be f of x equals x cubed, right? That has a 0 derivative at x equals 0, but it's neither a minimum nor a maximum. What does that look like when I map Rn to R? Well, let's take a look in 2 dimensions. So here I have a function that has a 0 gradient or a 0 tangent plane. And in fact, where that plane is tangential, right, I have a minimum, right? It's right there at the bottom. Similarly, this function has a maximum, and the tangent plane at that maximum is horizontal. In other words, the gradient there is 0. However, let's consider the reason why a saddle point is called a saddle point. This looks like a saddle. We're all from Texas. We know what a saddle looks like. But where the gradient is 0, I have neither a max nor a min. Because if I look upon the spine of the horse, right, if I were to put the saddle on a horse, along the spine it looks like a minimum. But perpendicular to the spine, right, if I look along the rib cages, it looks like a maximum. But still, at the intersection of these 2 points, the tangential plane is flat. In other words, the gradient is 0. But I have neither a min nor a max. So let's prove the statement. So let's prove the first derivative test. Suppose that x naught is a relative extrema, so a max or a min. Now, suppose, for the sake of contradiction, that the derivative of f at x naught, which is equal to the gradient of f at x naught transpose, is not 0. Well, let d equal the normalized gradient my idea is to show that if x follows in a positive d direction, I'll increase, and if it goes in a negative d direction, I'll decrease. Why do I think that's going to happen? Well, remember that d is the direction of steepest ascent. By the way, that because of continuity, that necessarily means that negative d is the direction of steepest descent. Now, since x naught is a relative minimum or maximum, there exists an R such that b of x naught R is contained in U. That's because of the openness of U. And f of x is less than or equal to f of x naught for all x in this ball or f of x is greater than f of x naught. Again, for all x in this open ball. Now, note that the derivative of f of x naught times d equals the gradient transpose at x naught times d, well, d is the gradient of f of x naught divided by the norm. And because this is an inner product, it's the norm squared, so I just get the norm of f of x naught, which is non-zero, right? We're assuming, right, again for the sake of contradiction, that this is not zero. So the norm of it is strictly positive. Now the differentiability at x naught implies there exists a delta, and I can choose delta to be less than r, such that if x equals x naught plus td, where t in absolute value is less than delta. Now remember that d is a unit vector. So if t is smaller in magnitude than delta, then x is within delta of x naught, which means I get that f of x minus f of x naught minus the derivative at x naught times x minus x naught in absolute value divided by the norm x minus x naught is less than, well, it's less than whatever I want, right? Whatever I want, there's a delta that'll give me my condition. Let's make it less than half the gradient at x naught in magnitude. Well, x minus x naught, if x is defined by this, is just t times d. So I can rearrange this to be f of x minus f of x naught minus, now if this is t times d, well then it's t times this, and I know how much that, right, I know what that size is, so I get t times the gradient of f at x naught is less than, now what is this? X minus x naught is t times d. The norm of that is the absolute value of t, right, and I'm going to multiply to the other side, times the norm of d, which is 1, right, because d has been normalized, times the norm of the gradient divided by 2. Now, remember, t is any number whose absolute value is less than the positive number delta. Suppose, right, I have an absolute value. And by the way, what does this mean? This means that the argument inside the absolute value is strictly less than this, but also strictly greater than the negative of this. And so we're going to use that fact, f of x minus f of x naught minus t, the gradient of f of x naught, is less than the absolute value of t times the norm of the gradient divided by 2, and it's greater than the negative magnitude of t, magnitude of the gradient divided by 2. I can take this term and add it to both sides. This would give me t minus the absolute value of t times the norm of the gradient divided by 2 is less than f of x minus f of x naught is less than t plus the absolute value of t times the gradient norm divided by 2. Well, I'm missing a 2 here. Let's put this over common denominator, and that we'll see why the 2 exists. The 2 should be there. Now, suppose that t is positive. Well, if t is positive, then 2t minus t, if it's positive, this is t, the absolute value of t is just itself. I just get t, and I get that this is positive, so I get 0 is less than t times the norm of the gradient divided by 2 is less than f of x minus f of x naught, which implies that f of x naught is less than f of x, meaning f of x naught cannot be a local maximum. Now suppose t is negative. If t is negative, right, 2t plus its absolute value would give me 1t, which is negative. Then I would have f of x minus f of x naught is less than negative absolute value of t times the norm of the gradient divided by 2, which is less than 0, implying that f of x is less than f of x naught. That means f of x naught cannot be a local min. So I've shown that there's an x, right, inside my ball that is both greater than f of x naught and less than f of x naught, meaning f of x naught is not a local extrema, but I assume that it's a local extrema, right? That's what I started with. So that contradicts the fact that x naught is local extrema. So it's not possible that x naught is a local extrema and the derivative at x naught is not 0. So we've proven our result. So let's work out an example. Let's show that if x naught minimizes, f of x is equal to x transpose a, b, b, c times x plus d, e transpose times x plus c. Let's make that g. I already have a c here. Let's add a 1/2. Then x naught solves AB, BC times x equals negative D, negative E. Notice that my matrix in this quadratic term is symmetric. Now, notice that if I had A, B, D, and C, this would still be a bilinear function. However, that function can be rewritten with a symmetric matrix and give me the same value. So this would be a good challenge to see if you could show that for yourself. So f of x is, if I multiply this out, I'll get 1/2 a times x1 squared plus 2 times b times x1 times x2 plus c times x2 squared plus d times x1 plus e times x2 plus g. So the derivative of f with respect to x1 equals ax1 plus bx2, right? This 2 cancels with this 2 when I took this derivative, and this 2 cancels with this. The derivative with respect to x1 of this is 0, right? So plus d. The derivative of f with respect to x2, that is b times x1 plus c times x2 plus e. So if x0 minimizes f, right, and f is defined for all of r, so the derivative of f at x0 equals to 0, which is equivalent to saying that the gradient of f at x0 is equal to 0. Of course, the gradient has as a first entry this and a second entry this. So the gradient of f at x0, well, notice that that's just the matrix A, B, B, C times x0 plus d, e. And that's equal to 0, which implies that my quadratic matrix term, AB, BC, times x0 is negative d, negative e. So in fact, to satisfy what are called first order optimality conditions, or the first derivative test, if I want to find my critical points, then it's equivalent to solving a matrix equation, which makes sense because if I want to minimize a quadratic, I should solve a linear to find where the derivative is 0, because the derivative of a quadratic is linear. Now, of course, you might think that now that we've done the first derivative test, what about the second derivative test? Well, in Calculus 1, the second derivative test involved determining when the second derivative was positive or negative or 0. However, here we're going to be dealing with a second derivative that has the form of a matrix. So we need to give an analogy for a positive or negative second derivative. So let's define positive definite and negative definite. A bilinear map from Rn by Rn to R, or the matrix associated with the bilinear map, is called positive definite if, for all x, x transpose times my matrix times x is positive. Or I can think of it as a bilinear map B of x, x. Now if I replace that inequality with a greater than or equal to, then I get semi-positive definite. And of course, negative definite is when that x transpose bx is negative for all non-zero x. And if I replace it with a less than or equal to, then I get semi-negative definite. So the bilinear map bxx, which we can think of as x transpose times mbx, where mb is symmetric, is positive definite if and only if all of the eigenvalues of MB are positive. We get semi-positive definite if the eigenvalues are non-negative. The symmetric matrix is negative definite if and only if all of the eigenvalues are negative. And semi-negative definite if the eigenvalues are non-positive. And my matrix is indefinite, which is to say none of the above, if and only if there are both positive and negative eigenvalues of my symmetric matrix. Now, of course, I should mention that a symmetric matrix is guaranteed to have real eigenvalues, so don't have to worry about dealing with complex eigenvalues in this situation. So let's prove the first bullet, and the second and third bullets are very similar. So let's prove the fact that a symmetric matrix is positive definite if and only if all of its eigenvalues are strictly positive. So suppose that my matrix, again we're supposing that it's symmetric. Well, that implies that my matrix is unitarily diagonalizable. Right? What that means is that V transpose V is the identity, which is to say that the columns of V, which are eigenvectors, can be chosen to be orthonormal. Right? And lambda is a diagonal matrix where the entries are eigenvalues. So all symmetric matrices can be diagonalized unitarily. In other words, the eigenvector matrix can be chosen to be a unitary matrix, meaning that V transpose V is the identity. That's the definition of a unitary, a real unitary matrix. Now, suppose that all my eigenvalues are strictly positive. Let X be non-zero. Then X transpose MBX equals X transpose V lambda V transpose X. Let me call this vector Z. Then this equals Z transpose lambda Z. And because lambda is a diagonal matrix, this equals the sum lambda J Zj squared. And of course, since this is positive, we assumed, Zj squared is going to be, at least for one of the entries, positive, because X is not zero. This is strictly positive. And since X was an arbitrary non-zero vector, we've proved positive definiteness. Now, suppose that my matrix is positive definite. Well, by the way, a symmetric matrix is guaranteed to have real eigenvalues. So this is a well-formed statement to say that each of these are greater than zero. Right? If these were complex numbers, it wouldn't be clear what is meant by these numbers are greater than zero if I'm in a complex plane. Okay? But again, a symmetric matrix is guaranteed to have real eigenvalues. So suppose MB is positive definite. Let V be an eigenvector, which are non-zero by definition. Then V transpose MBV is positive, and MBV equals lambda V. And this is lambda times the norm of V squared. And since that is not zero, this implies that lambda must be positive. Of course, if all my eigenvalues were negative, it would be straightforward in the same way to show that my matrix is therefore negative definite, and the bilinear form associated with it is also negative definite. I'll leave it as an exercise to show that if I have both positive and negative eigenvalues, then I'm indefinite, which is to say neither positive definite or positive or negative definite. Even if I add a semi-negative definite or semi-positive definite, none of these could occur if I have both positive and negative eigenvalues of a symmetric matrix. So now we have the tool to describe the second derivative test. Let F map an open set U and Rn to R be of class C2, and let x naught be a critical point. In other words, the derivative there is 0. Then if the second derivative is negative definite, then F has a local maximum at x naught. Now, if x naught is a local maximum, then the second derivative is semi-negative definite, at least. Of course, as you might imagine, there's a variation for positive definite. If my matrix is positive definite, then I have a local minimum. And if x naught is a local minimum, then my Hessian matrix is semi-positive definite. So let's give a sketch of the proof for the first iteration of the second derivative test. The second one follows by just multiplying by -1. Before we continue with that proof sketch, let's mention the indefinite case. If the Hessian is indefinite, then x naught is a saddle point. That is a critical point that is neither a local min nor a local max. So let's give a quick sketch of the proof of the second derivative test. Let's look at the first bullet. From Taylor, we get that f of x minus f of x naught is equal to the derivative of f at x naught times x minus x naught plus 1/2 times the second derivative of f at some value c times the 2-tuple x minus x naught. Now, I know that this term is 0 because x naught is a critical point. And my second derivative is a bilinear form, which has the structure x minus x naught transpose times the Hessian evaluated at c of f times x minus x naught. Hf of x, in other words, the Hessian as a function of x, this is the second derivative, right? It's equivalent to the second derivative of f at x is continuous. Right? It's continuous because I assumed that my function is of class C2, which means I can take two derivatives and each of those two derivatives are continuous. So I know that Hf of x naught is negative definite. Okay, but that's not where I'm computing the Hessian. I'm computing the Hessian at C, right? Some nearby point. Now, all I have to do is show that f has a local max at x naught. In other words, right, f of x naught has to be king of the hill, but the size of the hill doesn't really matter, right? It's got to be the biggest in its neighborhood, but I can just choose a neighborhood so that c is close to x naught, or that this is also negative definite. In other words, I can view this entire function as a function of c, And as x gets close enough to x naught, c also gets close enough to x naught that this becomes negative definite. Right? So I can choose x sufficiently close to x naught that my Hessian evaluated at C is negative definite. Is negative definite, implying that for such a close enough x, and C is between x and x naught, this is negative, meaning f of x is less than f of x naught, right? So f of x naught is a maximum, right, for all x sufficiently close. Now, for the second bullet, we suppose that x naught is a local max. Then g of t defined by f of x naught plus t x has a local max at t equals to 0. Right? Because of course g is equal to f, but just along a particular path, right? It's going from x naught in the x direction, right, as a function of t. Well, the second derivative of g evaluated at 0 equals x transpose times the Hessian of f at x naught times x. But here, because g is a real valued function of a real number, I can just use the second derivative test of calculus 1 and say that because g has a local max, this is less than or equal to 0, and x is arbitrary, which gives us our result. So again, this is a sketch of the proof. If you would like to see the details fleshed out, I would encourage you to read that section of the book, but for the sake of time, we'll have to move forward. So now let's consider local minima or maxima subject to a constraint. So we'll consider the constrained optimization problem, minimize or maximize f of x. F of x is known as the objective function, such that g of x is equal to c. So g of x equals to c is considered our constraint equation. So suppose both f and g map an open set in Rn to R. Both are of class C1. If x naught solves the optimization problem and the gradient of g is not 0 there, then the vectors, the gradient of f at x naught and the gradient of g at x naught are parallel, which means that they're equal to a scaling of each other, and that scaling is called the Lagrange multiplier. So I'm going to give a sketch of the proof here, but it's important that we get the ideas of the proof. So in order to make sure that we do get the ideas, I'm going to give it side by side with an illustration. So suppose x naught is a solution to the constrained optimization problem. In other words, x naught satisfies g of x naught is c, and it minimizes or maximizes f. Well, all x satisfying the constraint g of x equals to c is called the feasibility region. But notice, all x satisfying g of x equals to c, well, that's precisely the definition of a level set. So suppose g of x is equal to the norm of x squared. This is just an example. We can see the level set if I chose c is equal to 2. Right, we see here all x satisfying g of x is equal to 2 is given by a circle. Okay, so that circle is my feasibility region. And let's let this dot here that just popped up, let's let that be our x naught. Okay, we're going to predict the future a bit and say that that is the maximum of my objective function f on the feasibility region. So the direction of steepest ascent of g is perpendicular to the level set. And recall that the direction of steepest ascent is given by the direction of the gradient. So I'm saying that the gradient of g is perpendicular to the level set. Well, that might come as a little bit of a surprise, but if we think of the gradient as being a way of describing the tangent plane, well, if the tangent plane is tilted in a way that the level set kind of slices horizontally through it, then of course the direction of steepest ascent would be perpendicular to that line that you're rotating the tangent plane. So let's take a look at our function. Right, that red line is tangential to the curve, right? You see I have a curve, it's a circle, and that red line is tangential to it. Then if I were to add to this the gradient, you see the gradient, which is a vector in the domain, is given by this red arrow. And notice that this red arrow is perpendicular to the tangent line, which is to say that it's perpendicular to the curve at this point. And in fact, if I evaluate g in that direction, I get this red line, and we can see that it is the direction of steepest ascent. Right, that if I'm here and I want to increase fastest, then I would go in that direction. Okay, so we see an illustration of this fact. Let's see the mathematics proven out. Let gamma of t be any differentiable parameterized curve in the level set. Now, for this case, the level set is a curve, which we could parameterize by cosine of t, sine of t. Right, that would give us a parameterization of the curve. Of course, if we were in higher dimensions, then the level set will look like higher dimensional manifolds. If we were mapping R3 to R, the level set would look like a surface near x naught. But here it's a circle, and in fact we know what the parameterization is. So suppose gamma of t is one of those parameterizations. And let's arrange it so that gamma of 0 is x naught. Again, given my example, I could actually pick the parameterization cosine of t, sine of t, and when I evaluate at t equals to 0, I'd get exactly that red point. Now, g evaluated on this curve is c. Of course, we can see that because, right, my evaluation of g on this red curve is exactly where it slices with g equals to 2. So if I take the derivative of g of gamma of t, well, I'll get 0. Of course, the derivative of this is given by the chain rule. It's the derivative of g at gamma times gamma prime. The derivative of g is the gradient transpose, again evaluated at gamma prime. Now, gamma prime of t, that's a tangent, right? The derivative of a parameterized curve is a tangent vector to the curve. Again, this is equal to the derivative of c, which we know to be 0. So now, if I evaluate at t equals to 0, gamma of 0 is x naught. So the gradient of gamma of x naught transpose times gamma prime of 0, that is an errant equal, you should disregard it. This is actually multiplication, is equal to 0. And since this vector transpose times this vector is 0, then they are perpendicular. But remember that gamma was just an arbitrary curve, and because the gradient is perpendicular to all curves, it's perpendicular to the level set. Okay. So again, this part in bold is the main idea. The direction of steepest ascent of G is perpendicular to the level set. Now the direction of steepest ascent of F, which is perpendicular to its own level set, by the way, is also perpendicular to the level set of G at x naught. Okay, so let's take a look at that. Let's add our objective function. So here I have in the domain, of course, my axis. I have my region of feasibility, or my level set. And this is the gradient of G at x naught. Right, we should see that the gradient of f at x naught is going to be parallel to this vector. Right, that's what we should conclude. So here's f. I chose as my objective function a saddle because they're fun. So the red is my feasibility region. So let's evaluate f on the feasibility region. And that would give us the magenta curve. Okay, so the magenta curve is f evaluated on the feasibility region. Right, so we can see, right, I get exactly the circle, right, which is the level set of G, which is also the feasibility region. So all I really want to do is maximize the magenta curve, right? That's my only goal, is to maximize the magenta curve. Well, I claim the direction of steepest ascent of f, right, is going to be perpendicular to this curve. And in fact, we should see that, right, the direction of steepest ascent is going to be, right, going this way along the spine of the horse, if we think of this as a saddle. So let's see that worked out. The derivative of f of gamma of t, now it's got to be 0 when I evaluate at t equals to 0, because f of gamma of t is a local maximum. Right, we can see here f of gamma of t is a local maximum, or in generality a local minimum. It's either a min or a max, which means the derivative with respect to t should be 0, because this is just a scalar function of a scalar t. So that implies the gradient of f at gamma of t transpose times the derivative of the gradient at t equals to 0 is 0. So again, I get that the tangent, right, represented by gamma prime of t, but at t equals to 0, is perpendicular to the direction of steepest ascent. You see the direction of steepest ascent for f is given by this magenta vector. And of course it's right on top of the red vector. And if you look here, right, here's this direction of steepest ascent for f, right, when I evaluate f along it. So, of course, they're perpendicular. Gamma prime of 0, this is the tangent to the curve here. The gradient of f of x naught, that's the direction of steepest ascent here. And we can see that, in fact, they are perpendicular. Right? Just as the calculus predicts. So because the gradient of f and the gradient of g both evaluated at x naught, because they're both perpendicular to the level set at x naught, then they are parallel, which is our sketch of the proof of the Lagrange Multiplier Theorem. That's it for today.